Hello.
Actually, it's so simple.
All right, let's get started with class. Some announcements. Chapter 5, Achieve, is going to be posted later today, and that will be due next Monday at 9. We'll finish Chapter 5 this week, so we just have one Achieve homework for Chapter 5. There are 2 days stated in the syllabus where we don't have recitation. This Wednesday is the second one, so the first one we've already passed. So no recitation this Wednesday. And then my office hours Wednesday are at 2 this week, so 2 to 3 p.m. I do still have my office hours today at 1 o'clock if you want to stop by. I will have your assessments for you on Wednesday, so I'll run the Scantrons today. I'll update your exam score in Blackboard tonight or tomorrow, and then you'll have them on Wednesday. I usually don't like to update your scores before I pass them back to you, but I think it's important for midterm grades that your grade is most up to date as possible. So that's why we're doing it this way. So I will have those all for you on Wednesday. I think those are all of my announcements. Our next exam isn't for like 4 weeks, I think, so we've got some time for that. Okay, so let's do a little bit of a review of what we covered at the end of class last Wednesday. So we talked about limiting reactants. When we have amounts of multiple reactants provided, before we can do any stoichiometry to determine what amount of products are going to be produced, we have to determine which reagent is our limiting reagent, which reagent will limit how much of the product can be produced. So there are 3 different ways to do this. We've talked about the first 2 ways. The third way is still definitely possible. You'll be able to get the right answer, but it requires a few more steps that kind of complicates something that doesn't need to be complicated. So method 1 and method 2, we've already done these slides. Method 1, you take the amount of both reagents and do a separate calculation to see how many moles of one product will be produced. So in this case, we chose CO2. CO2 is a product, H2O is a product. You could pick H2O, that's fine too. You just need to pick the same product. Whichever calculation gives you the lower amount of product formed, you know that starting material is your limiting reactant. So that was the first method. The second method is taking the mole amount of the limiting or of both reactants, dividing by its coefficient, and whichever result is lower, that also tells you what your limiting reactant is. So this one's a little bit quicker, simpler calculation, but this one, if you're trying to find the amount of some product formed, you've already calculated the mole amount, so it can be productive depending on what the question is. So then we completed this question. This was the last thing we did on Wednesday, where we had determined on the previous slide that oxygen was limiting. We determined how many moles of carbon dioxide was produced, how many moles of water was produced. And since methanol, CH3OH, was the reactant in excess, we determined how many of the moles of methanol was used to react with our limiting reactant, and then we use that to determine how many moles of methanol are remaining. So we started with 1.5 moles, we used 0.333, and so 1.67 moles were left over after the limiting reactant was used up. So we're going to jump right in and do an iClicker question. So we have a chemical reaction. You might double check that this is balanced. We have 0.750 moles of hydrofluoric acid and 0.250 moles of sodium hydroxide. Your first question, and this is the first thing that you should do after determining your reaction is balanced, is to identify the limiting reactant. So you could use either method. And then whatever reactant is in excess, your second question is to determine how much of that reactant is used up so that you can answer how much of that reactant remains. So all three of those are different iClicker questions. So yeah, let's get started. Let me know if you've got questions about limiting reactants or any of these calculations. Yeah, I'll just plan to pick it up tomorrow. That's a question.
What's your favorite color?
It's like this color. A lot of my items are that color. We do. Like my shoes are currently that color. What's your favorite color?
I like orange.
Orange?
I'm trying to figure it out.
I do. I have a puppy. No, she's like, oh, I don't got color color. I do.
Save my camera roll.
Yeah, but that's
Oh,
not.
really?
That's my memory, bro.
This question is over.
Right?
Maybe 1 or 2 more minutes. Yeah, 0 points.
Yeah. Oh my God.
Okay, 1 more minute. So the time says 8:20 up there. We'll be done. Let me know if you're stuck.
Oh. Bro, the guy when he was that's like whatever you want to. I want to see if you're interested in joining that. Well, we should probably. And this guy is just running. He said, yeah, we're just running like.
So you could still use the same process. Like where you determine if somebody will, one of the processes is more based on both about. And then, oh, I gave you an extra minute now. Okay, let's say 30 seconds. At least get 1 submitted. Ten seconds. All right, closing it here. See how we did. All right, we got some mixed responses for all three questions. So in this particular reaction, our molar ratios, these are all coefficients of 1. So if our coefficients are 1, that means that our reactants react in a 1-to-1 molar ratio. So we can do the calculations to determine limiting reactant, and I will do that. But we can also look at how much of each starting material is present. We have 0.250 moles of sodium hydroxide, 0.750 moles of hydrofluoric acid. They react in a 1-to-1 ratio, so the max amount of sodium hydroxide that can be reacted is 0.250. That's also the max amount of hydrofluoric acid that can be reacted. So the lower mole amount when you have a 1-to-1 ratio of the starting material will be the limiting reactant. Well, let's do the calculations just to make sure. So step 1, determine limiting reactant. So if we start with hydrofluoric acid, 0.750 moles of hydrofluoric acid are present, and we're going to use method 1 where we determine how many moles of one of the products is produced. You could select sodium fluoride or H2O, either is fine. Let's just do sodium fluoride. My pen will write. For every 1 mole of sodium fluoride produced, 1 mole of hydrofluoric acid is used. So 0.750 moles of hydrofluoric acid would produce 0.750 moles of sodium fluoride. We use the same calculation with our molar amount of sodium hydroxide. So we start with 0.250 moles of NaOH. For every 1 mole of NaOH used up, 1 mole of sodium fluoride is produced. So 0.250 moles of sodium hydroxide produces 0.250 moles of sodium fluoride. So our amount of sodium fluoride, 0.250 moles present, produces a lower amount of, sodium hydroxide that's present produces a lower amount of sodium fluoride. This means this is the maximum amount of sodium fluoride that can be produced when we have 0.750 moles of hydrofluoric acid and 0.250 moles of sodium hydroxide present. Sodium hydroxide is limiting the amount of product produced, so that means that sodium hydroxide is our limiting reactant. And hydrofluoric acid is in excess. So step 1, determining limiting reactant. Any questions on this first part? Okay, now step 2, We're looking to see how much of the excess reactant remains, so how many moles of hydrofluoric acid is not reacted. We need to determine how many moles of hydrofluoric acid is reacted. And we base all of our stoichiometry calculations on the limiting reactant. So 0.250 moles of sodium hydroxide are reacted. For every 1 mole of sodium hydroxide reacted, 1 mole of hydrofluoric acid is reacted. So 0.250 moles of hydrofluoric acid is reacted, is consumed, or used up. Yes.
Why are you solving the hydrogen?
Here?
Yes.
Because the question is how much of the excess reactant remains. So we determined in the first part that sodium hydroxide is our limiting reactant. So we need to find, since hydrofluoric acid is in excess, how much of the 0.750 moles reacts with 0.250 moles of sodium hydroxide. So we know 0.250 moles of hydrofluoric acid is reacted. So that means the amount of hydrofluoric acid remaining is the total amount, 0.750 moles, minus the amount used, 0.250 moles, so 0.500 moles HF remains. So this means once the reaction is complete, you will have used up all of the sodium hydroxide because that's our limiting reactant. You use up some of the excess reactant, and you'd have 0.500 moles of the excess reactant present at the end of the reaction. Other questions on this? All right. The next slide is a flow chart that's in the book. The next example, sometimes when you're doing limiting reactant questions, you're not given the moles of the reactant amounts, you're given grams. When we're in a lab, we're not taking a sample to a scale and measuring moles, we're measuring mass. So oftentimes that's how our stoichiometry equations are starting off, is by mass. So if you have the masses of both reactants, you need to convert the masses to moles and then determine which one is limiting and which one's in excess. And then you can use the balanced chemical equation using the limiting reactant to determine the moles of product that's produced. And if you want to determine mass, then use molar mass to convert to grams. So this next question is another limiting reactant question. In this case, we're given grams of sodium bicarbonate and grams of sulfuric acid. So those are the two reagents, sulfuric acid, sodium bicarbonate. We're looking to find what mass of sodium sulfate will be formed when you measure 14.4 grams of sodium bicarbonate, 4.90 grams of sulfuric acid, add them together. One of these reactants will be in excess, one will be limiting. So the first step is to determine which of these is a limiting reactant. Since you're going to be calculating the mass of this product, sodium sulfate. The method that we've been using to determine which one's limiting by calculating moles of product produced, you might as well use the moles, see how many moles of sodium sulfate you produce with each amount of starting material. Once you determine your limiting reactant, you're halfway done with your second calculation, or more than halfway done. So anyways, the iClicker question is just determining which reactant is limiting. So I'll get this started, work on that, and then continue working on the question to determine the mass of sodium sulfate produced. Oh, let me give you molar masses actually. So you need molar mass of sodium bicarbonate. I'll write all of these up here. Molar mass of sodium bicarbonate. So molar mass of sodium bicarbonate, I'm assuming you all can calculate molar masses. We're just adding the atomic masses of every element in the formula. So that sodium bicarbonate, what's the other one? Sulfuric acid is 98.07. And then you're calculating mass of sodium sulfate. So I'll give you molar mass of sodium sulfate. And that is 142.05 grams per mole. Spend another minute or two. If you haven't determined the limiting reactant, make sure you start with that, answer that I-clicker question, and then submit. It's the only clicker question, and then continue with the rest of the question. And do you want me to just look at it? Oh, and then there's.
He wasn't a judge, no.
Okay, let's say 30 more seconds. I think there's about 6 of you that have submitted. All right, we're gonna stop it here. Okay. So I had a question. Could we take these amounts and divide by the coefficient to determine which is limiting? In this case, since we have grams, we can't divide by the molar coefficient. You'd have to first convert to moles of each reactant and then divide by the coefficient. That's a fine method to use as long as you're working in molar amounts. I'm going to use the other method where we calculate the moles of one of the products produced to determine which amount of reactant produces a lower mole amount of the product. Since the question is to determine the mass of sodium sulfate, then I'm going to determine the moles of sodium sulfate to determine the amount of that produced. You could also, by determining limiting reactant, you could just calculate how many grams of sodium sulfate is produced with each amount. Whichever amount is lower, that's the amount that's going to be produced. But if we're just determining limiting reactant, we have 14.4 grams of sodium bicarbonate. Convert to moles of sodium bicarbonate. And our molar mass is 84.01 grams. And then we use the coefficient ratio. So for every 2 moles of sodium bicarbonate, we produce 1 mole of sodium sulfate. And so this would produce 0.0845 moles of sodium sulfate. And we use the same process to determine how many moles of sodium sulfate would be produced with 4.90 grams of H2SO4. We use molar mass. We use the molar ratio. 1 mole of sodium sulfate is produced for every 1 mole of sulfuric acid used. So with this calculation, we're producing 0.0500 moles of sodium sulfate. So the first step, determining limiting reactant. We've calculated molar amounts of sodium sulfate produced with each reactant. We see that the amount of sulfuric acid produces less sodium sulfate. So that means sulfuric acid is our limiting reactant. Sodium bicarbonate is in excess. Second part of the question is determining the mass of sodium sulfate produced. Well, we already know how many moles of sodium sulfate are produced, so we can just convert 0.0500 moles. Using its molar mass, 142.05 grams. And if we simplify, this is 7.10 grams of sodium sulfate. So we have to determine which reactant is limiting. If we just went with sodium bicarbonate and said we produce 0.084 moles of sodium sulfate, then we'd have a higher number here than what is actually produced. We'd start with 0.0845. We'd have a higher gram amount produced, but that's incorrect because the amount of sodium sulfate that is produced is limited by the amount of sulfuric acid present. Questions on all of this? I see some of you are writing, so I'll give you some time. All right, I'm going to go to the next slide. Remember, you can always look at the recordings if you need to. Okay, so the next 2 slides are just a review of this section. The whole section was about limiting reactants. A reaction will proceed until the reactant in lower molar ratio quantity is used up, or when our limiting reactant is used up. We have an excess reactant. Whenever we're calculating how much product is produced, we need to use the amount of the limiting reactant provided. And then there are 3 ways to determine which reactant is limiting. We talked about the first 2. As I mentioned earlier, the third one is just more complicated than we need to make this calculation. It's still, if that makes conceptual sense to you, you can use the third method. That's totally fine. Our next section is on theoretical yield and percent yield. Have you all been calculating percent yield in your labs? Yeah, okay. So that's about as complicated as we're getting for this section. It's really not too bad. But the whole idea behind it is that, well, all of the stoichiometry calculations that we've done so far, the product amounts that we're calculating are the theoretical amounts that could be produced if nothing goes wrong, if every single amount of product is measured on the scale in the lab. But in reality, many reactions will stop before they're completely finished, before all of the limiting reactant is completely used up. Some other, if you're adding some reactants to a flask, there could be competing reactions that will use up some of the reactants, and so you're not producing the theoretical yield of product. You could lose some product during collection or purification. Like if you do a reaction in a beaker and then you produce a solid and you need to filter out the solid, or you need to transfer the solid to a weigh paper to weigh the product amount, some solid might be left over in the beaker and you're not calculating the full amount that's produced. So we have, through stoichiometry, through calculations, we have calculated the theoretical yield. That's the maximum amount of product that could be produced. And usually what's actually measured in a lab is less than the theoretical amount. If it's more than the theoretical amount, you probably don't have a pure product. You've got something else present. So we use percent yield to determine relatively how much of the theoretical amount is produced and collected. So percent yield, we take the actual amount, so that's the actual amount that's produced and measured in a lab, divided by the theoretical amount, which is what we calculate using reaction stoichiometry, so the maximum amount that could be produced, and then multiply it by 100. So we'll do one example question here. A lab technician calculated that a reaction should yield 25.4 grams of magnesium oxide. This is the calculated maximum amount that could be produced. So this is the theoretical yield. Theoretically, if everything goes perfect, this amount of product should be produced. When she did the reaction, measured the product, she obtained 16.7 grams of magnesium oxide. So this is what is actually produced and collected in lab. So this is the actual amount. And question is, what's our percent yield? So we just use our percent yield calculation formula. We do actual amount divided by theoretical times 100%. Our actual amount, 16.7 grams. Theoretical amount is 25.4 grams. Multiply by 100%, and this is 65.7% yield of MgO. Now, when you're doing these calculations, it's important that the actual yield and the theoretical yield are in the same units. So if one is in moles and one is in grams, you can't do this percent yield calculation directly. You have to convert the moles to grams or the grams to moles. As long as they're in the same unit, you can, and for the same desired product, you can calculate the percent yield. Let's go ahead and do this question. So here is another, it's going to be an iClicker. Percent yield question. So someone does a reaction, percent yield is 86%. 5 grams were expected to be produced. The question is, how many grams were actually produced? So 5 grams is, oops, theoretical, and you're looking for the actual yield. $30. Five seconds if you want to get an answer in. All right. Okay, kind of a mix. So we can use our percent yield equation to calculate, to solve for the actual yield. So we're given that the percent yield is 86.0. And this is equal to the actual yield, which we don't know. So we'll just use X. Theoretical yield is 5.0 grams. Multiply by 100. And then we're solving an algebraic equation. So you could divide each side by 100%. Then you get 0.860 equals x over 5. Solve for x. You could simplify this side. Say we have x times 100 divided by 5. There are a couple different ways to solve it. I'll divide by 100% on both sides. So we get 0.860 equals x over 5.0 grams. So now we're multiplying by 5.0 grams on both sides. And you would get X is equal to 4.3 grams. Okay, questions on this calculation? All right, I've posted the chapter 5 part 2 PowerPoint on Blackboard. We'll start with that on Wednesday, so make sure you have that printed or downloaded for class.